Representation of functions by power series, section 9.9. Recall creating an infinite geometric series of the form n goes from 0 to infinity, a sub 1 times r to the n. Why n equals 0? Because the first term does not require multiplying by the common ratio. Also remember that if the absolute value of r is less than 1, then our series has a sum, it converges, and we can find that sum. So we know that if a sub 1 is 2 and r is 3, I get 2 times 3 to the 0, 2 times 3 to the 1, 2 times 3 to the second, 2 times 3 to the third, and so forth. And if a1 is 5 and r is negative 2, I get 5 times negative 2 to the 0 times negative 2 to the 1 times negative 2 to the third, 2 times negative 2 to the third, and so forth. A power series is a series of variables involving x to the n. Now let's remember, a p series involves a series of constants to a power. That's a p series. This is not a power series. X is more powerful than a constant. Okay? X is more powerful than a constant. X to a power. If a function can be written in the form a1 over 1 minus r, we can find its power series by recognizing it as a geometric series of the form n from 0 to infinity, a1 times r to the n. Okay, for these examples, again, as I ask each time, let me explain it, and then at the end of it, I'll give you time to write it down. Find a power series for f of x equals 1 over 1 minus x squared, centered at 0, and find its interval of convergence. You will notice we have it of this form. So that makes our a1 to be 1, and r is x squared. So I need to find a power series for it, and my power series I'm going to generate using what we know about geometric series. So here's my a1 plus a1 times r to the 1 plus a1 times r squared plus a1 times r to the third, and so forth. Okay. So what I get is this. And now we must generate how to write that series. Notice that x squared to the n gives x to the 2n. Notice that when n is 1, I have my exponent to be 2. When n is 2, my exponent is 4. When n is 3, my exponent is 6. That's how we came up with x to the 2n. And this is why we had to look at section 9.1 to figure out with our pattern what can we come up with. That was the whole purpose for that section. So we know that this is a geometric series and it is going to converge when the absolute value of r is less than 1. So that is, of course, is going to be when x squared absolute value is less than 1. And the problem that we have here is you can't just take the square root of everything, because we cannot take the square root of -1. So we have to do a little bit of algebra. Also, we know that since we're squaring, whatever x is, when we square it, will be not negative. So I really don't have to look at this part. I have to look at this part. You cannot just take the square root of both sides, but what we can do is subtract 1 and factor it. Now, way back ago in Algebra 2 and in pre-cal, you should have learned how to do this. And of course, we've done this process in calculus. So we want to know where this product is negative. So we'll pick test values. We know that x cannot equal -1 or 1. This is where this is 0, and we need it to be less than 0. But it does divide our numbers up into the numbers before -1, between -1 and 1, and after 1. And we need to know where that product is negative. Well, I can do my test, and it's right here, from -1 to 1. So that gives our interval of convergence to be from -1 to 1. Now, what is our radius? Well, it looks like we are centered at 0. We were told at the beginning we were centered at 0. We know we're centered at 0 because we do not have the quantity x minus c squared written down here. So our radius is 1. Now, let's remember there are lots of ways to write a series. It depends on where your index starts. Take a moment to write down the work in this example. Again, let me explain the problem. Then you can write it down in a moment. Find a power series for g of x, 1 over 4 plus x, centered at 0, and find its interval of convergence. Well, first of all, this must be in the form a1 over 1 minus r. So the first thing we need to do is write that as 1 over 4 minus negative x, because this has to be a negative. The next thing we have to tackle is this has to be a 1. How do we make this a 1? We divide every single term in the whole fraction by 4. When we do that, we get 1/4 over 1 minus negative x to the 4th. This makes a 1 to be 1/4, and it makes our r to be negative x over 4. So now let's build our power series. A1 times r to the 1 minus x over 16 times r again, or I can think of it as a1 times r squared. But anyway, multiplying this by negative x to the 4th gives us a positive x squared over 64. Multiplying by negative x to the 4th again gives us a negative x cubed over 256, plus so forth. Now let's build our series. We've written some terms. What can we see? Well, a1 is 1/4, r is negative x over 4, and if I look at this, this looks like x to the first power, x to the second, x to the third. So starting at 0 lets me write x to the n. I could have also written this like this. That negative here could have become -1 to the n, x to the n over 4 to the n, or -1 to the n times x over 4 to the n. I could also have thought about it like this. I have my denominators of 4. I could have written this as -1 to the n, x to the n over 4 to the n plus 1. Okay. Are any of these better than the first one? No. Let's go ahead and find our interval of convergence. So here is our absolute value of our ratio less than 1. Puts us in this interval, multiply by 4. Okay, pause the video and take a moment to write down this work. Again, let me get through the explanation and then you can write down the work. Find a power series for f of x equals 3 over 2x minus 1 centered at c equals 2. Now c equals 2 means we want x minus 2 and find its interval of convergence. So we've got a lot of things going on here. First thing we can see is I need my sum in the form of a1 over 1 minus r. So the first thing we might want to do is rewrite this as 3 over -1 plus 2x. Now I got a lot going on here. We got to get x minus 2 in there. -1 plus 2 times, now I need x minus 2, so I'm going to change that x to the quantity x minus 2, and let's remember, what did I do here? I added a -4, so I have to offset that by adding back in a +4. Now, if I can do the next step, which is -1 plus 4 is 3, and this needs to have a negative sign in front of it. So I need to write this as minus -2 times x minus 2. What's the next step? That needs to be a 1. So everything is going to get divided by 3. Every term, this term, and I pick a factor here. Obviously, I'm going to pick the constant. So from here, I can see that a1 is 1, and r is all of that, -2/3 times x minus 2. there's what I'm going to work with. Let's list out some terms. So we are rewriting this. Okay, so that's 1. Now, when I multiply my A1 by one factor of this, I get negative 2/3 x minus 2. This has a negative in it, so I'm going to multiply by negative again. That is going to become, that will be positive. This is 4/9, and this is x minus 2 squared. Multiply by negative 2/3, that's going to give me negative 8 over 27, x minus 2 cubed. You see where this is going? And so our series can be written as n equals 0 to infinity of my A1 times my r, and it looks like if I start at 0, then it's r to the n. We have to find our interval of convergence, so r, absolute value, has to be less than 1. That makes our inequality this. How do I fix that? Well, I multiply by 3/2, right? And add 2. So there's my interval of convergence, but my radius is 3/2 because we're centered at x equals 2. That's the key thing to remember. Just remember, we're centered at 2. How far is 7/2 away from 2, which is 4/2? 3/2. Take a moment and write all of this work down. Last example for this video, the final example on this page will be done after we have gone through the next section. So we'll come back and revisit this page. Number 4, again, let me explain the example before you write it all down. Find a power series centered at 0 for the function 3x minus 1 over x squared minus 1. Oops, that's different from all of them because look, I got something on top. And not only that, I don't have a linear denominator. We have a non-constant numerator. We might have arrived at this by adding fractions. We have to do partial fractions. So we know that x squared minus 1 factors to x plus 1 and x minus 1. I'm not going to insult you by showing how to get the work, but by partial fractions, we get these. I know you know how to do that, so I will not insult your intelligence. But if you want to be sure, go ahead and go find it just to make sure you still remember how to do that. And now we're going to treat each one of these differently. We're going to work with the first fraction. In our first fraction, again, we want the 1, we need the constant first, and that would make up minus a negative x. My A1 is 2, so here is my series listing it out, 2 minus 2 times x, multiply that by negative x, we get plus 2x squared minus 2x cubed, and so forth. And if we start at 0, so that this is 1 and this is x to the 0, we are looking at the series 2 times negative x to the n goes from 0 to infinity. You could also write it like this. Now let's look at the second term. I'm going to do the same thing, which is negative 1 plus x. That is, I can do something kind of interesting here. Factoring negative 1 out of here gives me that desired 1 minus r. And this negative 1 down here can actually just be slid up to the numerator. So my A1 is negative 1, my r is x. So negative 1 multiplied by x, multiplied by x, multiplied by x, and we get this series. Now here's what's cool. I had this fraction plus this fraction, and I got this series, and we're going to add it to this series. So this is one reason that it's important that you have the same index. All right, so adding these two together is going to give me 2 times negative 1 to the n times x to the n plus negative 1 times x to the n. Now let's list out what this series becomes. So this can become when, so I'm going to list term by term. When n is 0, I get 2 minus 1. When n is 1, I get 2 times negative 1 times x plus -1 times x gives me 3x. And you can go through that process and see that you get this. Very nice, neat problem. I could then find the interval of convergence and all of that work. I'll leave that to you. This next example will be done after we have covered section 9.10, Taylor and Maclaurin series. So take a moment to write down all this work. Your TPs for this section are 5, 7, 13, and 16. Yes, I know there's an even one in there. It's a good problem. See you next time.